Next 11. An alternating voltage E equal to 320 sin of 314t is applied across a resistance. Resistance is 16 ohm. The RMS value of current is So the given circuit is in this question. The given circuit is resistive circuit. In the resistive circuit, we need to calculate the RMS value of current. RMS value of current, IRMS, is equal to VRMS divided by R. Okay, or IRMS is equal to the relation between RMS value, RMS voltage and the peak voltage is VRMS is equal to Vm divided by root 2. So therefore, IRMS is equal to Vm divided by root 2 into R. Vm divided by root 2 into R. Right? Instantaneous voltage equation is given. E is equal to 320 sin 314t. The instantaneous voltage in the resistive circuit is given to E is equal to Em sin of or Em or SPE. V is equal to Vm sin of omega into t. Comparing these two equations, Vm value is 320 and R value is given, that is 16 ohm. So substitute the resistance value 16 and the peak voltage 320 in this equation. Therefore, RMS current in the resistive circuit is Vm value 320 divided by root 2 into R value 16. 20. 1 divided by root 2, 0.707 or 2 into 7.07. So 2 into 7.07, 14.14 ampere. In the resistive circuit, relation between RMS current and RMS voltage is IRMS is equal to VRMS divided by R. Therefore, IRMS is equal to relation between RMS value and the peak value is VRMS equal to Vm divided by root 2. Therefore, Vm divided by root 2 into R. Comparing these two equations, Vm value is 320 and resistance value is 16 ohm. Substitute the two values in this equation, we can get IRMS value. IRMS value is 14.14 ampere. Right, B option. A coil of resistance is 300 ohm and inductance 1 Henry is connected across an alternating voltage of frequency 320 divided by 2 pi hertz. 322 divided by 2 pi hertz. The phase difference between the voltage and the current in the circuit is. The phase difference between voltage and the current is. Right, here the coil has both the resistance and also self-inductance. So it becomes like a series combination of inductor and resistor is connected to the AC source like this. This is inductor and this is a resistor. Right. Generally, the phase difference between, for example, in LCR circuit, the phase difference between current and voltage is given by pi is equal to tan inverse of XL minus XC divided by R. In LCR series circuit, the phase difference between current and voltage is given by pi is equal to tan inverse of XL minus XC divided by R. But in this circuit, there is no capacitor. So, capacitive reactance is taken as 0. Then this equation becomes pi is equal to tan inverse of XL divided by R. XL divided by R. Right. XL is equal to omega into A. XL equal to omega into A. Omega 2 pi F into A. Right. Therefore, 2 pi into frequency value is given, that is 300 divided by 2 pi. And self-inductance value is 1 Henry. So XL is equal to 300 ohm. Right? And the resistance value is 300 ohm. Resistance R also 300 ohm. Substitute XL value R value here. Then phase difference between voltage and the current pi is equal to tan inverse of XL value 300 and R value also 300. So tan inverse of 1. Tan inverse of 1, 45 degree. So phase difference between voltage and the current in the circuit is 45 degree. The number of turns in primary and secondary of a transformer are 1000 and 3000 respectively. If 80 volt AC is applied to the primary, the potential difference per turn across the secondary. Potential difference per turn across the secondary would be. First, stored the given values. Number of turns in the primary is 1000 and number of turns in the secondary is 3000. And the primary voltage VP is equal to 80 volts. Okay, we need to calculate potential difference per turn across the secondary. That is Vs divided by EMS value wants to find out. Vs, the total voltage across the secondary coil. Total voltage across the secondary coil. If the total voltage across the secondary coil is divided by the total number of turns in the secondary coil, that gives voltage per turn. Voltage per turn. Right. So first we need to calculate the total voltage in the secondary coil. For that, we can use the transformer ratio condition. That is Ns divided by Np is equal to Vs divided by Vp. Ns divided by Np is equal to Vs divided by Vp. Therefore, Vs is equal to Ns divided by Np into V. Number of turns in the secondary 3000 and number of turns in the primary 1000 into primary voltage is 80. So 3 8s are 24, so 240 volt. So this is total voltage in the secondary coil, but we need to calculate the total voltage per turn, voltage per turn across the secondary coil. So therefore, Vs divided by Ns is equal to 240 divided by secondary turns 3000. 100. So 8 divided by 100, 0.08. 8 volt. So this is voltage or potential difference per turn of the secondary coil. That value is 0.08 volt. 240 the total voltage in the secondary coil. This is primary and this is secondary. So the total voltage across the secondary coil Vs value is 240 volt. The potential per turn of the secondary coil is just 0.08 volt. Next. In an AC circuit, V and I are given by V is equal to 100 sine of 100 t volts and I is equal to 100 sine of 100 t plus 5 by 3 milliampere. The power dissipated in the circuit. Power dissipated means the average power consumed by the circuit. Average power consumed by the circuit. The average power consumed by the circuit is ERMS into cos pi. ERMS into cos pi or VRMS into cos pi. Or otherwise VRMS can be written as Vm divided by root 2. IRMS can be written as Im divided by root 2 into cos pi. Or Vm Im divided by 2 into cos pi. Right. From this equations, that is V is equal to 100 sine. Given value V is equal to 100 sine of 100 t. This equation is compared with V is equal to Vm sine omega t. So comparing these two, Vm value is 100 volt. Vm is 100 volt. Right. Similarly, current equation I is equal to 100 sine of 100 t plus pi by 3. And I is equal to Im sine of omega t plus pi by 3. Now comparing these two equations, Im value is 100. But here in the equation, the current value is given in milliampere. So 100 milliampere. IM value is 100 milliampere. Right. Now substitute IM value and VM value in this equation. And what is the phase relation between voltage and current in the circuit? Pi by 3. Which one lead? Current leads the voltage by the phase angle of pi by 3. So phase value pi by 3. Pi by 3 is nothing but 60 degree. IM equal to 100 milliampere and VM equal to 100 volt. Then power dissipation VAV is equal to VM value 100 and IM value 100 milli 10 power minus 3 divided by 2 into cos 60. Cos 60 1 by 2. Right. So 15 into 50 2500 into 10 power minus 3. So 2.5 power watt. Power dissipated or average power consumed by this AC circuit is 2.5 watts. C option. In the given circuit, what will be the reading of voltmeter? Right. So this is RLC series circuit. Just to look at the RLC series circuit, the voltage across the inductor and the voltage across the capacitors are same. VL is equal to VC. When the voltage across the inductor and voltage across the capacitors are same at the resonance condition. So the circuit is in a resonance condition. At the resonance, the entire applied voltage appears across only a resistor. The applied voltage is 200 volt. The entire 200 voltage appears only across the resistor. So the voltage, there is a voltmeter is connected across the resistor. The reading of the voltmeter is applied voltage. So 200 volt. At the resonance condition, there is no voltage across the inductor. Actually, the voltages exist across the inductor and the capacitor. The two voltages are 180 degree out of phase. So the net voltage across these two is 0. The net voltage across inductor and the capacitor is 0. So the entire applied voltage is always appears only across the resistor. So the voltage across the resistor is 200 volt, which is read by voltmeter. So voltmeter reading is 200 volts. Question number 16. The resonant frequency of a circuit is F. If the capacitance is made 4 times the initial value, then the resonant frequency will become. In RLC series circuit, the resonant frequency is given by F is equal to 1 divided by 2 pi into square root of LC, resonant frequency. If the capacitance value changes, then the resonant frequency value also changes. Now, the new capacitance is taken as a C prime, which is equal to 4 times of initial value. Right. If the capacitance value is 4 times of C, so automatically the resonant frequency value also changes. The new resonant frequency is taken as F prime, which is equal to 1 divided by 2 pi into square root of L into C prime. Self-inductance does not change, only capacitance value alone changes. Right. Therefore, F prime is equal to 1 divided by 2 pi into square root of L. C prime is equal to 4 times of C. Right. 1 by 2 pi into square root of LC, square root of 4, 2. Therefore, 1 divided by 2 into 1 divided by 2 pi into square root of LC is F. Therefore, F prime is equal to F divided by 2. If the capacitance of the capacitor is made 4 times that of initial value, the resonant frequency becomes off. Resonant frequency becomes off. B option. A coil of area 500 cm square with 1000 turns is placed such that the plane of the coil is perpendicular to the magnetic field. If the coil is rotated through 180 degree in 1 by 10 seconds, the EMF induced is 90 millivolt. Then the magnetic field value is right. Here the EMF is induced by changing the position of the coil. By changing the position of the coil, right? Induced in the coil, general formula E is equal to minus d pi by dt. Pi is equal to NBA theta, MBA cos theta, or minus of pi 2 minus pi 1 divided by t. Initially, the coil is placed so that, in the magnetic field, so that the plane of the coil is perpendicular to the magnetic field. If the plane of the coil is perpendicular to the magnetic field, means the normal to the plane of the coil is parallel to the magnetic field. So initially, the angle between normal to the plane of the coil and the direction of magnetic field is 0 degree. After that, the coil is rotated through 180 degree. So the final angle is theta 2, which is equal to 180 degree. Right now, the induced EMF E is equal to minus of final flux can be written as NBA into cos theta, NBA into cos theta 2, right? Minus initial flux can be written as NBA into cos theta 1 divided by T, right? Minus of NBA cos theta 2 value is 180 degree, so cos 180 minus 1 minus NBA into theta 1 value is 0 degree, so cos 0 1 divided by T, right? That is equal to minus of minus NBA divided by T. Minus NBA minus 2 NBA divided by T. Minus into minus plus, so 2 NBA divided by T. Right? Now substitute the given values, number of turns, 1000 turns, and magnetic field value is, okay, magnetic field value wants to calculate, and EMF induced in the coil is 90 millivolt, and next area of the coil is 500 centimeter square, and time is 1 by 10 seconds. So number of turns 1000, magnetic field value wants to calculate, and the area of the coil is 500 centimeter square, and EMF value is 90 millivolt, and time value is 1 divided by 10 seconds. Right? EMF 90 or 9 into 10 power minus 2 volt, 2 into number of turns 1000 or 10 power plus 3, and magnetic field value you need to find out, and the area 500 centimeter square or 5 into 10 power minus 2 meter square, right, divided by 1 by 10. Right, 10 goes to numerator, so 10 power minus 2, 10 power minus 2 cancel. So 9 is equal to 5 to 10 into 10 into 10 power plus 3 into B. Right, therefore B is equal to 9 divided by 10 power 3 into 10, 10 power 4, 10 power 4 into 10, 10 power 5. So 10 power 5 or 9 into 10 power minus 5 Tesla or Weber per meter square. The magnetic field is 9 into 10 power minus 5 Weber per meter square, or 0.9 into 10 power minus 4 Weber per meter square. Option 4th option. Flux formula pi is equal to NBA cos theta. D pi can be written as final flux minus initial flux divided by time. Right. Initially, the coil is placed so that the plane of the coil is perpendicular to the magnetic field. Then angle between normal to the plane of the coil and the direction of magnetic field is 0 degree. Again, the coil is rotated through 180 degree. So final angle is 180 degree. So EMF induced in terms of changing position of the coil is given by E is equal to minus NBA into cos theta 2 minus NBA into cos theta 1. So substituting theta 2 value and theta 1 value, we can get minus 2 NBA divided by T. N value, A value, T value and EMF value are given. From that we can calculate magnetic field value. The magnetic field value obtained is 0.9 into 10 power minus 4 Weber per meter. 220 volt, 50 Hz source is applied to the LCR circuit containing inductive reactance 8 ohm and impedance is 10 ohm. Then the value of quality factor is. First, what is quality factor? Quality factor is a term which is used to measure the sharpness or selectivity of a series resonance circuit. So here the circuit, LCR circuit is in resonance condition. right? At the resonance condition, inductive reactance is equal to capacitive reactance, and the impedance of the circuit becomes minimum, which is equal to ohmic resistance. We know that the quality factor Q is equal to the ratio of voltage across the inductor to the or capacitor to the applied voltage. Voltage across inductor is VL, which is equal to I into XL divided by entire applied voltage appears across resistor. So applied voltage is equal to voltage across resistor. So I into XL divided by voltage across resistor VR can be written as I into R. So I cancel. Right. XL value is given, that is 8 ohm, and the impedance value also given, that is 10 ohm. At the resonant, the impedance value is equal to ohmic resistance. So XL value 8 and R value is equal to impedance value, that is 10. So 8 divided by 10, 0.8. No unit. Quality factor value is 0.8. Consider the situation shown in figure. If the switch closed and after some time it is open again, the closed loop will show. Option A, an anti-clockwise current pulse. B option, a clockwise current pulse. C option, an anti-clockwise current pulse and the clockwise current pulse. And last option, a clockwise current pulse and the anti-clockwise current pulse. Right. So if the switch is closed, then current starts to flows in this circuit. That current changes from 0 to certain STD value, that is a maximum value. So whenever the switch is closed, okay, the battery sends an electric current through the circuit, which is changes from 0 to maximum, right? If the current is flows through the circuit, magnetic field is produced around it. That magnetic field is also linked with the closed loop, because the loop lies very close to the circuit. So the magnetic field is also linked with the closed loop, right? So here the current changes from 0 to maximum. So that is why the magnetic field linked with the closed loop also changes from 0 to maximum. So there is a change in magnetic flux which is linked with the loop. So induced current is produced in the loop. The induced current is always oppose the increasing magnetic field. Because according to Lenz, the direction of induced current is always oppose the cause. Here, due to the increasing magnetic field, induced current is produced in the loop. That induced current is oppose the increasing magnetic field. So to oppose the increasing magnetic field, the magnetic field due to the induced current must act opposite to the direction of magnetic field produced by the current flows through the current. So first, what is the direction of a magnetic field acting inside the loop? Want to find out by using the right hand corkscrew. Maxwell's right hand corkscrew rule, right? According to Maxwell's right hand corkscrew rule, here the current flows downward direction. By applying Maxwell's right hand corkscrew rule, the direction of a magnetic field passing through this loop is outward direction. That is perpendicular to the plane of the board and outward direction. So magnetic fields are acting like this. The magnetic field due to the induced current must act opposite to the direction of the magnetic field produced by this current. So that magnetic field should be acts perpendicular to the plane of the board and inwards. So the magnetic field due to the induced current is acting perpendicular to the plane of the invert. By applying right hand thumb rule, the direction of induced current produced in the loop can be determined. So by applying Fleming's right hand thumb rule, the direction of magnetic field is clockwise. The direction of induced current is clockwise direction. If the key is closed, the current flowing through the circuit increases, so the magnetic flux linked with the loop also increases. So due to the change in magnetic field, induced current is produced in this loop. So that induced current must act opposite to the direction of the magnetic field produced by this steady current. So that is by applying right hand thumb rule, the direction of induced current is along the clockwise direction. Along clockwise direction in first case. Right. After some time, the switch is open. If the switch is open, the current flowing through the circuit changes from maximum to 0. The current flowing through the circuit changes from maximum to 0. So the magnetic field linked with the closed loop also changes from maximum to 0. Maximum to 0. Again, there is a change in magnetic flux which is linked with the loop. Again, induced current is produced in the loop. Now, this induced current must act along the direction of the magnetic field produced by the current. So, by once again applying right hand thumb rule, the direction of induced current should be as anti-clockwise direction. In second case, anti-clockwise direction. So, when the key is closed, the direction of induced current produced in the loop is clockwise direction, and the switch is open, the direction of induced current produced in the loop becomes anti-clockwise direction. Right? The correct option is D option. First clockwise current pulse and then anti-clockwise current pulse. Right? And last problem. An AC voltage represented by E is equal to 310 sin 314t is connected in series to a 24 ohm resistor and 0.1 Henry inductor and a 25 microfarad capacitor. The reactance of the circuit. What is reactance of the circuit? The difference between inductive reactance and capacitive reactance is nothing but reactance or net reactance. So net reactance is XL minus XC or XC minus XL. If a predominant is inductor, the inductive reactance is greater than capacitive reactance, so the net reactance is given by XL minus XC. Suppose in the LCR circuit, capacitor is predominant, then capacitive reactance is more than inductive reactance, then net reactance becomes XC minus XL. Right? So XL minus XC value which to calculate. Right? Formula for XL, omega into L. L value is given in this question, that is 0.1 Henry. And from this instantaneous voltage equation, omega value is 314t. Omega value is 314. Therefore, XL is equal to omega 314 into L value 0.1. So, XL is equal to 31.4 ohm. Inductive reactance value is 31.4 ohm. Similarly, capacitive reactance Xc is equal to 1 divided by C omega. Right? C value 25 microfarad. Right? C is 25 microfarad or 25 into 10 power minus 6 farad. And omega value same 314 radian per second. So Xc is equal to 1 divided by 314 into 25 into 10 power minus 6. Right. After simplification, Xc value becomes 127.4. So Xc value 127.4 ohm and XL value is 31.4 ohm. Here Xc value is more than inductive reactance value. So in the LCR circuit, predominant is a capacitor. Then net reactance Xc minus XL. Xc value 127.4 minus XL value 31.4. Right? Different 96. So reactance value is 96.